Hello learners, welcome to this course on embedded system design using PIC16F877 Microcontroller. In this tutorial, I will be discussing about on how to interface a stepper motor with 16F877 microcontroller. First, let us start understanding the fundamentals of a stepper motor. A stepper motor, it translates electrical pulses into mechanical movement. So when we apply a voltage or current to a stepper motor, it converts this electrical signal into mechanical movement. It is a brushless DC electric motor that divides a full rotation into smaller number of steps. So full rotation, this is 360-degree rotation. So the 360-degree rotation is divided into number of equal steps. So its main application is in disk drives, dot matrix printers, and in robotics. So if you see the construction of a stepper motor, it has a permanent rotor, permanent magnet rotor at the center, and it is surrounded by the stator windings, 4 stator windings. So these 4 stator windings can be connected in a center tapped fashion, which means I can connect the 2 coils at one end and we can take it as a common terminal. So here, for example, A and B are connected together on one end and it is taken as a common terminal. Same way, C and D coil at one side we connect it together and take it as a common terminal. So the other ends A, B, C, D can be connected to a microcontroller. So why do we need to do this type of connection? Why do I need to connect one end of the coil with the other end of the another coil and take it as a common terminal? So this allows the change of current direction in each of the 2 coils. So for example, if my B is set to be 0, then the current can flow from A, it can pass on to this coil and it can go to B coil and it will get grounded. Whereas if I set A to be 0, in that case the current will go from B coil, it goes into the A coil and gets grounded. So thereby the change of current direction can be achieved. So if the change of current direction is achieved, thereby the magnetic field produced will also change its polarity. So depending upon that, the rotor will get aligned to that magnetic field. So this stepper motor, we can able to achieve small steps but without any feedback mechanism, without any sensors attached to the shaft. So it is not a closed loop mechanism, it's an open loop mechanism. So we can able to achieve to an extent the accuracy in positioning the shaft to a particular angle in an open loop controller mechanism. So here I show a construction of a stepper motor. So here we have this part is a rotor and here we have the stator windings. So the stator windings will produce a magnetic field and the rotor will get aligned to that magnetic field. So this is the complete construction of your stepper motor. So we have different ways in which we can excite the stepper motor. So first let me talk about single phase 4-step sequence. So single phase in the sense at a time only one coil will get excited, and in order to get a 360-degree rotation we are going to make 4 steps. So that is why it is called a single phase 4-step sequence. So here we have a rotor at the center, movable rotor, and we have 4 stator windings A, B, A dash and B dash. So first let us take, we are going to excite the coil A. So let us assume the current is going to flow from top to bottom. So thereby the magnetic field will be induced from bottom to top. So then the rotor will get aligned to this magnetic field. So let us assume the rotor is assigned. On top we have the north pole and on the south we have on the bottom we have the south pole. So next we will try to excite the coil B. So again from right to left the current starts flowing. So the magnetic field will be from left to right. So now the rotor will move from this position to the new magnetic field position. It gets aligned to the new magnetic field. So thereby the rotor comes to this position. So thereby we get a 90-degree rotation from previous step to current step. Next we try to excite coil A dash. So when the coil A dash is excited, the magnetic field will be from top to bottom. So and the rotor again makes a movement of 90 degree and gets aligned to the magnetic field. Next B dash will be excited. Again the rotor makes a movement of 90 degree and it gets aligned to the magnetic field. So here we are exciting the coil in the sequence of first coil A is excited, next coil B is excited, next coil A dash and next coil B dash. So which means our rotor makes a clockwise rotation. If I change the order of coil excitation, for example, if I first excite coil A, then B dash, then A dash and B, which means now the rotor will move in the anti-clockwise direction. So just by changing the sequence of coil excitation, we can able to change the direction of your stepper motor. Second type of excitation is biphase 4-step sequence. So biphase in the sense at a time 2 coils will be excited simultaneously. So here first let us take coil A and B are excited, which means coil A will produce a magnetic field, same way coil B will produce a magnetic field, and we will get a resultant magnetic field in between coil A and coil B. So our rotor will get aligned to that resultant magnetic field. Next coil B and A dash will get excited, same way the rotor will get aligned to that magnetic field, resultant magnetic field. So you can see there is a 90-degree movement from the earlier step to the current step. Next coil A dash and B dash and then B dash and A. So thereby we take 4 steps to complete 360-degree rotation. So now this is for clockwise direction. If I want to excite the stepper motor in anti-clockwise direction, first A, B dash will be excited, next B dash, A dash will be excited, next A dash, B and B and A. So thereby we can achieve anti-clockwise rotation. So just by changing the sequence of order of excitation of the stator coils, we can change the direction of rotation. If I want more steps, in that case we can go with 8-step sequence, off-step sequence. So here what we do, first we excite coil A alone. So thereby the rotor gets aligned to that magnetic field. Next coil A and B together gets excited. So we get a resultant magnetic field. So now the rotor moves 45 degrees along clockwise direction. Next coil B alone is excited. So the rotor again moves 45 degrees and gets aligned with the B magnetic field. Next B and A dash, then A dash alone, then A dash and B dash, then B dash alone, then finally B dash A. So thereby we take 8 steps to complete one full rotation in the clockwise direction. Again by changing the coil excitation procedure, we can have the change in the direction of your stepper motor movement. If I want still more number of steps, if I want still more than 100 steps or 200 steps, what we can do? We can change the voltage applied to each coil. Instead of having a fixed coil voltage, I can vary this voltage. So thereby the magnetic field produced will change. For example, let us take, I am going to give a 1 volt to coil A, thereby a magnetic field will be produced and it will be a weak magnetic field. Next I will increase it to 2 volt, 3 volt, 5 volt. Let us go on to 5 volt. So the magnetic field will be produced will be maximum. Then what we do? We try to increase the voltage for your coil B from 0 to 1 volt, which means A is producing a strong magnetic field, B is producing a weak magnetic field. So now the rotor will make a movement, but it will be closer to the coil A. Then I start increasing the coil B voltage to 2 volt. Then little bit stronger it becomes the magnetic field. So now there is a slight movement towards B. Then 3 volt, 4 volt, 5 volt. When it reaches 5 volt, coil A voltage and coil B voltage both are 5 volt. So both are going to produce the magnetic field of same intensity. So we will get a resultant magnetic field along the diagonal between A and B. Next, I will start decreasing A. From 5 volt, I reduce it to 4 volt. So then what happens? The magnetic field produced by B becomes more intense. So thereby the rotor starts moving towards coil B. So when I start decreasing coil A voltage from 4 volt, it goes to 3 volt, 2 volt, 1 volt, 0 volt. Then the rotor will get aligned to your B. So thereby I can achieve more number of steps. So by changing the coil excitation voltage or current, I can able to get more number of steps. Another method for getting more number of steps is by putting the teeth onto the rotor and the stators. Thereby we can achieve more number of steps. So a step angle. What is step angle? So step angle is determined by the internal construction of the motor. So step angle is nothing but the smallest step or how much movement, how much rotary movement we can achieve in one step. So in particular, the number of teeth on a stator. So the step angle, it mainly depends upon the number of teeth on a stator and the rotor. So the step angle is nothing but minimum degree of rotation associated with a single step. In a single step, how much angle it moves. That is nothing but the step angle. So for example, if I have 500 steps per revolution, so one revolution is equal to 360 degrees. If I have 500 steps in 360 degrees, then for one step, how much angle it will move? 500 divided by 360 divided by 500. So that gives about 0.72 degrees. So each step of about 0.72 degrees movement is achieved. Same way, if I have number of steps per revolution is 200, then I have to do 360 degree divided by 200, which gives about to be 1.8 degree movement. So essentially what happens, if I do a 4-step sequence, if I excite the coil, stator windings in a 4-step sequence, how much movement is associated with it? So it associates only one rotor tooth pitch will be moved. If I complete a full rotation, right? Full rotation, this is 4 steps. So first I will excite coil A, B, A dash and B dash. So if I complete it, what happens? Only one rotor tooth pitch will be moved. In order to get a 360 degree rotation, let us assume I have a rotor with 50 teeth. So each teeth movement will have 4 steps. So totally I should have 200 steps for the complete 360 degree rotation. Let us assume our rotor has 50 tooth pitch. In order for one tooth pitch movement, I require 4 steps. Right? So in order to get a 360 degree rotation, it is nothing but 4 into 50, which is 200 steps are required. So what is the minimum step angle? Is always a function of number of teeth on the rotor. So if I have more number of teeth, then I will have a smaller step angle. If I have less number of teeth, then I have a larger step angle. Then how the motor speed is measured? So motor speed is measured in terms of steps per second. How many steps it can move in a second. So the steps per second equal to RPM of a motor into steps per revolution divided by 60. By using this formula, we can calculate the steps per second, the speed of the motor. So there are 3 common types of stepper motor: universal, unipolar and bipolar. So this is identified by the number of connections. So universal motor will have 8 leads, whereas a unipolar motor will have 6 leads. Bipolar motor we have 4 leads. So a universal motor has a 8 leads, unipolar motor has a 6 lead and bipolar motor has a 4 lead. So we can convert our universal motor into unipolar and bipolar. Unipolar can be converted to bipolar, but bipolar cannot be converted to universal and unipolar. So we can see the connections. If I take a bipolar connection, 4 lead bipolar connection, We have 4 leads are black, green, red and blue. So these are the 4 leads coming out of a bipolar stepper motor. In case of a 6 lead unipolar, I have black, green on one side of the coil and there is a center tap connection which is yellow color. And for the another coil we have red and blue on either side and the center tap we have a white color. So this is a 6 lead unipolar connection. We can convert this unipolar into a bipolar by leaving the common terminal with no connection. Okay, common terminal, if it is no connection, then it becomes a bipolar configuration. For a unipolar, we can have something like 8 leads, black and green on either side of the coil, and other 2 ends are yellow and orange. So this yellow and orange, it can be connected together to form a unipolar connection. As a center tapped connection, we can form it. Yellow and orange can be connected together and a common terminal can be taken. So thereby a universal motor can be converted into a unipolar motor. Same way here, white and brown terminals are interconnected and a common lead is taken. Same way 8 lead bipolar. So 8 leads are there, black, green, red, blue, and the center points are yellow and orange. So this yellow and orange are interconnected with each other and we are not going to take a common terminal, so thereby it becomes a bipolar connection. Same way here, white and brown are interconnected with each other, thereby it forms a bipolar connection. Then 8 lead bipolar parallel connection is, I have black, green, and these 2 coils, orange end is connected to black, yellow end is connected to green. Same way here, red and blue are the 2 sides of the coil and the center terminals like white and brown are, white is connected to blue, brown is connected to red terminal. So this is a 8 lead bipolar connection. So these are the 3 major types of stepper motors: universal, unipolar and a bipolar stepper motor. Now let us discuss about the programming part. So we are going to take PIC16F877 microcontroller and I am going to use a ULN 2003A motor driver. So this ULN 2003A is a high voltage, high current Darlington transistor arrays. Why it is required? Because the stepper motors might require higher voltage or higher currents. So those voltage and current cannot be supplied by your microcontroller. So in that case, I have to connect an external supply which needs to be diverted to your stepper motor. So it enables the low voltage, low current output of a microcontroller to drive a high current stepper motor. So thereby we make use of this ULN 2003A motor driver. And also it has another advantage that it provides an isolation between your microcontroller and the motor. Because whenever we have a rotating structure, this rotating structure will try to produce a back EMF. So this back EMF should not enter into your microcontroller, it might damage your microcontroller. So in order to have an isolation also, this ULN 2003A driver will be used. So in this project, what we are going to do is, we are going to connect port C, C0, C1, C2, C3 to 1B, 2B, 3B, 4B terminals of ULN 2003A and the corresponding outputs 1C, 2C, 3C, 4C goes to your stepper motor. And the stepper motor is connected with the power supply. So your logic 0 to the port lines will excite the coil of a stepper motor. Logic 1 will not excite the coil of a stepper motor. So a logic 0 will excite the coil. So we are going to use Micro C Pro for PIC as an integrated development environment, and where we will be writing our embedded C program, convert this embedded C program into a hexadecimal file. Then we will be using a Proteus 8 Professional to build the circuit, put that hexadecimal file onto this Proteus 8 environment and check whether our program is working properly or not. So let us go and start doing our circuit implementation. First let us start with Proteus 8. Let me create a new project. select a location for your project. I'll put it as stepper motor. Select a location for your project, give a name for the project. That also I'm going to give it a stepper motor. So the project is with an extension .pdsprj. Press next. Then I am going to use a default schematic. Press next. We are not going to create any PCB layout, so I am going to leave it as it is. And we are not going to use any firmware. So press next. So only schematic is selected. Press finish. So now the location where we are going to build the circuit is obtained. So now we have to select the components. So I go to PIC devices, PIC16F877. So I am going to select the IC, add it to the list here. Then I require a stepper motor. So here we have bipolar stepper motor and unipolar stepper motor. I am going to use a unipolar stepper motor which has 6 leads. You can see here, which has 6 leads. The 2 center points are common leads and the other leads are, it will be connected to your microcontroller. So add the stepper motor to your list. Then I require a crystal. Add it to the list. Capacitor. Add it to the list. Then I require a switch for reset operation. Switch gets added. Resistor gets added. I also require ULN 2003. So I try to take this high voltage, high current Darlington array. So here you can see the IC details of your ULN. Get added to your list. So these are some of the components I require. So once I selected all the components, press OK. Now let us make use of these components to build the circuit. So first let me start with the microcontroller. Place it onto the schematic. Then I need to connect the ULN. Select the ULN. I am going to connect it to RC0 to RC3. So I connect it here. So RC0 gets connected to 1B, RC1 connects to 2B, RC2 to 3B, RC3 to 4B. So 4 terminals I have taken, and I connect the stepper motor on the other side. So I connect 1C to one end of the stepper motor and another end I connect it to 2C. 3C is connected to another terminal of your stepper motor and 4C is connected to another terminal of your stepper motor. So the 2 common terminals I am going to connect it to supply. Go to terminals mode, select power, put it onto the circuit, connect it to the common terminal. So these 2 leads I am going to connect to the supply. So this completes the stepper motor interconnection. Now let us go and put the oscillator part. So go to components mode, select the crystal. I am going to rotate this crystal. So place it onto the circuit. Then connect this crystal to pin number 13 and pin number 14. Oscillator 1 and oscillator 2 pin. Then it also requires a 33 picofarad capacitor. So select the capacitor, place it onto the circuit. Then other end of the capacitors, I am going to ground it. So go to terminals mode, ground, place it onto the circuit, connect it with the capacitors. Now let me change the values of this capacitor. Right click on the component, edit properties. Let me put it as 33 picofarad. Same way for other component also. 33 picofarad. I am going to set the oscillator frequency to be 10 megahertz. Right click on the component, edit properties, 10 megahertz. Up to 20 megahertz we can connect. Here for this project I am going to use 10 megahertz. So this completes the oscillator part. Still a reset section should be connected. So I go to again components mode, select a switch. I am going to rotate it, place it onto the circuit. Then take a resistor, connect it with the switch. One end of the resistor is connected to the switch. Other end of the resistor, I am going to connect it to the supply. And the other end of the switch, I am going to connect it to ground. The center point, I am going to connect it to the memory clear pin. So what happens? This memory clear is an active low signal. So by default, this pin will be at high. Whenever I close the switch, the current will propagate to ground. Thereby, this terminal will come to 0 volt. Thereby, reset will take place. So this completes our circuit. So we have put the oscillator circuit, we have put the reset circuit, and we have connected the stepper motor with our microcontroller. Now let us go and save this project. Now let us move on to building the embedded C program. Let us go to micro C. So in micro C, first let me create a new project, a standard project, press next. So select a location for your project. So I am going to use this location, C users admin download work PIC micro. So the IC you need to select. So I am going to use PIC16F877 and the oscillator frequency is I am going to use a 10 megahertz. And give a name for the project. So the name for the project is STEPPER_motor. So we are selecting the location for the project, name for the project, select the microcontroller for which we are doing the program and select the device clock frequency. Press next. We don't have files right now, so I am going to press finish. So now this is the location where we are going to put our code. So let us save this code. Save the code in the name of stepper_motor.c. Save. So I have already written the program. So I will try to copy that program. Paste it onto this location. Save the program. So here I have declared two functions, stepper clock, stepper anti-clock. So this is for clockwise rotation and this is for anti-clockwise rotation. So in port C, I am going to use the lower 4 bits, C0, C1, C2, C3. I am going to use the lower 4 bits. So here you can see the 0 will excite the coil, 1 will not excite the coil. So which means C0 and C3 are excited. In the next condition, it is C3 and C2 are excited. In the next condition, C2 and C1 are excited. In the next state, C1 and C0 will be excited. Again, C0 and C3 will be excited. So here we are changing the logic of our coil excitation. Thereby, we will achieve a clockwise rotation. So let us take C3 to be top, C2 is on the right, C1 is on the bottom, C0 is on the left side. So which means C3 and C0. C3 and C0 in the sense the top and so C3, so the combination is C3, C2, C1, C0, right? So C3 is on the top. So for example here, so this instead of A we take it as C3. Instead of B dash it will be C2. A dash will be C1, B will be C0. Right? So first we will be exciting C3 and C0. So this is at the center. Next C0 and C1. Next will be C1 and C2. So thereby we get a clockwise rotation. So we get a clockwise rotation by this sequence by providing 6, 3, 9, C and 6, I get a clockwise rotation. Just by changing the order, I can get an anti-clockwise rotation. So here you see 6, C, 9, 3, 6, which means I get the opposite order. So here you can see first again C3 and C0 is excited. Next one is C0 and C1 is excited. Next one is C1 and C2, then C2 and C3. Again it goes back to the first statement. So we have defined two functions where a stepper clockwise rotation and stepper anti-clockwise rotation is written. Now we are going to call this program in our main program. So in a main, tris C equal to 0800, which means the port C is configured as an output port. And in a while loop, I call the stepper clockwise and I wait for some 2 seconds, then I call the anti-clockwise direction. So first the motor rotates in clockwise direction, then it changes the direction to anti-clockwise. Since it is in a while loop, again it goes to clockwise direction, then anti-clockwise. So it continues again and again. So after saving this program, let us build the program. So it has successfully built. Now let us go and import the file onto our Proteus environment. So right click on the IC, edit properties. So here I have to select the program file. So program file, let me go and select the program file. Micro C. So here I have stepper underscore motor. This is the exa file. Open. Then I have to set the processor clock frequency to be 10 megahertz. Press OK. Now we have imported the hexadecimal file onto the microcontroller. Now we have to check whether it is working properly or not. So press the play button. So you can see it starts rotating in clockwise direction. Then it will start moving in anti-clockwise direction. Now it starts rotating in anti-clockwise direction. So it takes 4 steps to complete one rotation. Again it goes back to clockwise rotation. Since it is in a while loop, it goes into the clockwise rotation. So thereby we can easily connect a stepper motor with a microcontroller and we can do the programming in both clockwise and anti-clockwise direction. So here we have used biphase 4-step sequence for a stepper motor. So in this tutorial, I have discussed about on how to interface a stepper motor with PIC16F877 Microcontroller. Thanks for watching. Please subscribe for more technical learning. Thank you.